Okay. So from here you can see the EMC number of the valence electrons for this one is 1, right? Yeah, because the proton number 3 minus 2, so it's 1. Okay. So in this case, we also can see this case. Okay, in this case, so how many neutrons, how many protons? 4. Okay, and the inner is 1s2. The outside, the valence electrons, 2s2, right? So what the ENC number? 2. Yes, 2. 4 minus 2, right? So it's equal to. In this case, so we know if the ES number is, this value is larger, so the attraction between the nucleus and the valence electrons are stronger. So this is why this is the size of this atom is smaller than this one. Okay. So this one, for this one, there are 5, right? And the 1s2, 2s2, 2p3. So the outside orbiter is 2, right? The layer of orbiter is 2. 2s2, 2p1. So what the ES number? Yes, it's equal 3. Because using 5 minus 2, so it's equal 3. So the attraction between the nucleus and the valence electrons are stronger than those two. So basically, it has small radius. Okay, this is why from left to right, the atomic radius decrease, because for the valence electrons, it has its ES number is become big, so the attraction between the nucleus and the valence electrons become stronger. Okay, so they are decrease. Okay. Okay, so this is why we can explain. We can using the ENC number to explain why in one period from left to right the radius decrease. Okay, here now we introduce the size of the iris. We know firstly the valence electrons also repel each other. For example, for this, they are in the same layer, right? In the same layer of orbiter. They also repel each other. Okay. And when an atom becomes an iris, the repulsion between the valence electrons increases. When here has more electrons, this means the repulsion between the valence electrons also increase. But here, ENC number change or not? Yeah, ENC number doesn't change. For example, in this case, what the ENC number for the valence? 7. For the valence is 7. It means 9 minus 2, right? So it's 7. 7 we know is large, right? It's large. So this is why the fluorine atom is very small. It's very small. But when it gets 1 electron here, so now here has at first the valence electrons is A, right? The number of valence electrons is A. It's 7. It's 7. Now is 8, right? It's 8. What is the ENC number for this? Change or not? Yeah, it's still the same, right? So this means from neutral to an iris, the ENC number doesn't change. This means the attraction from the nucleus doesn't change, right? Doesn't change. But what change? Just it has more electrons. It has more electrons. For example, at first it has 1, 2, 3, 4, 7, right? In one layer. When it gets, so they repatriate like this. They also repair each other. Anyway, so when Y electrons put in here, so we can see the repulsions between these electrons also increase, right?
Yes.
So and then it will bigger. It become bigger. So this is why when the atom get electrons, they are reduced increase, just because the ENC number doesn't change, but the repulsions between the valence electrons increase, so they have to become bigger. Okay, so now here we explain why an iris is always larger than the neutral atom. Okay. So we can see the change. For example, this is a neutral. This is atomic radii. This is neutral. They are neutral, right? And from left to right decrease, and from up and increase. Okay, but we can see their size change. Okay, so when they lose electrons, they become small, and when they get electrons, they become larger. And here we can. So we just we explained why iris is larger than neutral atom, and of course the cations is always small than their neutral atom. This is easy. I think this is easy to be understood, because for example, lithium at first it has 2 layers, right? When it lose the outside layer, and of course it's decrease, right? Because the layers changed from 2 to 1, and of course its size will decrease. So here we can see when the 1A group metals they lose electrons, they become small. But when they get electrons, the layers of the optics doesn't change. But when here has more electrons, the repulsions increase, so they will become bigger. Okay, and this slides show the why the cations always are small than their neutral atom, just lose from 2 layers to 1 layer. Okay, so basically they can, when they get electrons, get energy, they will lose this electron, and then it becomes small, right? So here we explained why cations are small, why ions are larger, right? Also why from left to right, small. And of course from up to down, definitely is larger, bigger, because they have more layers, right? Okay. So now we know the atomic radius, and we also know their changes. Why sometimes they change they change bigger, sometimes they change small. So here is about ionization energy. So ionization energy is the minimal energy required to remove an electron from a gaseous atom in its grounded state. So what this means? This means when we remove one electron from the atom, basically we should provide energy. So this energy is called ionization energy. Ionization energy. And of course, for one atom, it may lose more than one electrons. So basically, if they lose the first electron, it's called first ionization energy. And then they can continue to losing the second one, so it's called second ionization energy, and also the third. And of course, basically, the first is small, then second is smaller than third. Why? Because when it loses one electron, so it will has plus charge, and then the valence electron will attract by nuclear much stronger. So this is why the second one should be larger than the third one. And when it loses two electrons, and of course, it becomes more difficult to lose the third one or the fourth one. Okay. So basically, I1 less than I2 less than I3. So this table to show the ionization energy of the atom. So from here we can see. So basically, for low-bell gases, helium, and this AR, and basically their ionization energy are high, right? Why? For noble gases, their ionization energies are high. Why? Because they are stable, right? Yes. Because they are full orbitals. So they are stable. So this means when they're stable, of course, it's difficult to lose electrons. So you need to provide more energy to remove their electrons. And basically for the 1A group, lithium, sodium, right? And then this one, basically their energies are small. Why? They only has one electron, right, outside. So they are easy to lose. So you don't need to provide much energy. Okay, so basically they have low energy, ionization energy. And of course, basically it's easy to lose the first one. And if it lose the first one, it becomes stable, right? And so if you lose the second one, the energy is huge. Okay, lump of energy. And the third one is much difficult. And also for this, so the first one is small because it's very easy for them to lose one electron to form stable full orbital electron configuration. And when they become stable, so if they lose the second one, it's very, very difficult. So this is why the second energy and the third energy is become larger. Okay. So here to show the first ionization energy for all the elements. So from here we can see in this is one period. Okay, from left to right, it increases, right? From this in one period, from left to right, it increases. Why? Yes, because the size is small, right? From left to right. So if the size is small, this means the attractions between the nucleus and the valence electrons are strong, right? Are strong. So this is why they are ionization energy big. So in one group, from up to down, it's increase or decrease? Yes, decrease. See, this is one group. Why?
Increase the number of shells.
What?
Increase the number of shells.
Yes, increase the number of because the size also increase, right? So the attraction, it's if the the attraction also weaker, right? So from up to down, there are ionization energy decrease. Okay. So here we can see for the ionization energy from left to right increase because their size decrease. From up to down they decrease because their size increase. So the tense between the energy and the size is opposite. Okay, so this is about ionization energy. So here we introduce the electron affinity. So electron affinity is the elective of the energy change that occurs when electron is accepted by an atom. So here we can see when atom lose electron, you need to provide energy. But when one atom get the electron, basically, it will release energy. So release energy, this means the atom lose energy, right? So basically, we're using their minor data, the minor value. Then, so using the minor value to call like electron affinity. This is elective number. Okay. So for example, here, for example, for fluorine, if we get one electron, it will release 328 energy. Okay. So we just because if you lose, we should minus, right? But here we elective the energy. So here change to plus, change to positive. So this means if this number is big, it's large. So what does this mean? It will release more energy, right? More energy. So, for example, fluorine and oxygen, if we get one electron, it will also release this energy. Okay. So here we show this energy numbers. So from here we can see for these no metals, their number are larger than this one, right? Than this metal. Because we know for these no metals, they tend to get electrons, right?
Yeah.
So the tend to get electrons, this means they will release more energy. But for metals, basically they don't want to get electron. So when they get the electron, they just release very few energy. Okay. So here to show this affinity, electron affinity. So basically, in one period, so from left to right, it increase, right? It increase because the size is small and it will easy to get electron. Easy to get electron means when it get electron, it will release more energy. Okay. And basically from in one group. So this is basically a little change. Okay, but little. So for this guy has the highest one. Okay. Okay. So now we know why some atoms tend to get electrons, but some tend to lose electrons. Because when they get electrons, they may if they release more energy, so this means they tend to get. Because when an atom release energy, they have few energy. If they have few energy, this means they are stable. If they have high energy, this means they are active. They are active. Okay. And here we introduce the electron-activity. Electron-activity. So what is electron-activity? Yeah, electron-activity. So basic electron-activity is the ability of an atom in a molecule to attract shared electrons to itself. In this case, for example, we know this is in this molecule hydrogen. So these two atoms are same, right?
Yes.
So they have the same ability to attract the shared electrons. So the electrons are just occupied by these two atoms units. But in this case, we can see they also share one pair of electrons, but this pair of electrons are more close to fluorine. Because the fluorine has high electron activity than hydrogen. So it can attract more electrons. So the electron more close to the fluorine. So we can say the density of the electrons around the fluorine is higher than hydrogen. So this is decided by their electron activity.
So is that word electronegativity or electronegativity?
Electron.
Electro.
Electron activity.
Not electron.
I don't know how to, you can say the word here, all right? Okay, so here this table to show the number of the electron activity. Basically, so how to get these numbers? So these numbers are not obtained by experiment. No, we just calculate according to their electron configuration, like this, something like this, and the electron structures. We can calculate their electron activity. For example, we just put the fluorine. The fluorine is the highest one, and we just put its number is 4. Okay, it's 4, and then based on this number, we can calculate the electron activity of other atoms. And if the number is higher, this means they have more ability to attract electrons. Attract the shared electrons. Okay. So from here we can say the no metal basically have high electron activity number than the metals. Okay, so basically, for the electron activity, from left to right, it increase. Okay, the size decrease, and from down to up, also it increase. So this means if the size of the atom is small, it can attract electrons, shared electrons. Okay. If the size of the atom is large, so of course it's difficult to attract electrons. Because if large, this means the nucleus is too far away from the shared electrons. So they're difficult to attract the electrons. Okay. Yeah.
How do you calculate the electron getting into value?
Oh, if you want, maybe you need it's like structural chemistry. Structure is another course. Yeah, you need the whole semester. So you know, it's complicated.
So are we going to learn?
No, definitely. For example, our students, just for graduate students, maybe they can. For undergraduates, they also don't need to know how to calculate. You just need to know they are not from the experiments. They are from calculations. Yeah. So this is So in the same period, from left to right increase, and in the same group, from up to down it decrease. So here to show. So for electron affinity is obtained from the experiment, but for electron activity, it's just a relative number, okay? And they just calculate from the electron models. Okay, now the question: in carbon dioxide, which kind of atom attracts more shared electrons? Carbon? Carbon or oxygen? Oh, come on, someone said carbon. So basically, carbon and oxygen, which one has high electron activity?
Carbon.
Which one is bigger? If oxygen is bigger than carbon, but it is
Oxygen 3.5, carbon 2.5.
It's oxygen.
So definitely oxygen, right? So from left to right, this one is small, and this can attract electrons, shield electrons, other than carbon. So in this case, the answer should be the oxygen can attract the shield electrons, okay, more from the carbon. Okay. Now here we simply introduce the atomic properties. Atomic properties. So firstly, we just introduce the representative elements. Like for example, here the first one is about group 1A elements. So basically, the properties of elements are depend on their electron configuration. For example, for group 1A, its electron configuration is NS1, right? So NS1 means it's easy to lose this electron. So basically, it shows like a +1 charge, and it's very easy to lose this electron. So this means it's very active. It's very active. So when it, like for example, it can directly react with water, something like this, and form the compound. So usually they show the +1 charge, because they have low ionization energy, and also they have low electron activity. They have low ionization energy. It means they don't need much energy to lose the electron. They are easy to lose the electron. So basically, they show +1 charge. Okay, so these pictures are show the elements. For example, for 1A lithium and sodium, these elements they are very active. So you can keep them in the air, because in the air there's some oxygen and water, right? They they are easy to directly react with the water. So you must keep them in the oil, and especially for this, you must put them in the vacuum, okay, in the vacuum, because they are very stable, they are very active. Okay, group 2A. Group 2A, for these elements, they have NS2 charge, NS2 electron activity. So they also have low ionization energy, So this means they are easy to lose these 2 electrons and to form +2 charge. So also can directly react with water like this. Okay. So, but of course they are more stable than the 1A group elements. Okay. So most of them can stay in the air. But for this one, it's also very active. So Group 3A. So group 3 is these elements. So these elements also have low ionization energy. So they also easy to lose the electron to form +3 charge. Okay. All of them are also most of them are metals. Okay, and of course they are more stable than group 1A and 2A, so they can stay in the air. 4A are these elements. So they have medium ionization energy. So they can, and the electron capability is NS2, MP2. So they can lose all these 4 electrons, or they may also can to get 4 more electrons to form 4 orbital. So basically they can show like -4 charge. Also they may show +4 charge. And they also can show like just only lose these 2 MP2 electrons and to form +2 charge. Okay, so these photos show they are stays in environment. So we know the carbon, right? The carbon can have 2 states. One is like graphite, and the one is like diamond. Okay. Okay, this is about group 4A. Group 5A. So 5A, they also have medium ionization energy. So this means they also may get 3 more electrons, or lose all 5 electrons, or like 3 electrons. So they can show -3 charge, or they can show +5 or +3 charge. They also can react with water. But of course, they may need like heat. Okay, provide energy. Okay, so 5A. So this is the pictures of the 5A. So in this group, so these 2 are no metal, and these are metals. And with the nitrogen is a gas. Okay, 6A. Yes. So 6A are these elements. So most of them are no metals, and also they can show because they have medium ionization energy. So they can also show like they can get electrons or lose some electrons. So for example, they can show like -2 charge and +6 and +4 charge, +4 charge. So this is the photos of these elements in the environment. Okay, 7A. 7A is this group. So we know they are very small, right? So they have very high ionization energy. Very high ionization energy. Very high ionization energy means it's very difficult to lose electrons, right? If they lose electrons, you need to provide more energy. So this means basically they tend to get electrons. So usually they issue -1 charge. They can get 1 electron to form a compound with -1 charge. And most of them are also gases in room temperature. Okay, group AA. So this we know noble gases, right? So noble gases, of course, they also have high ionization energy because they are stable. So they don't want lose electrons. So basically, also they are stable. But sometimes they also can form compounds. They also can. It's not easy, but because we know fluorine it has a high ability to get electrons. So they can get electrons from the noble gases, and the noble gases also show the positive charge. Okay, so here we just very simply introduce the element properties of the representative elements. Yeah.
Question. Which element does highest ionization?
Which
Element has the largest lowest ionization energy?
low ionization.
The lowest.
Lost. So you can think which kind of elements want to lose. 1A. So sodium sometimes sodium, and should be this one. Okay, this one they have low ionization energy. These elements they NS1, right? NS1. So they tend to lose this electron, and this one has because it is larger, right? It's more easy to lose. Yeah. And basically, for example, for chemistry students, they learn also much more complicated about the properties. But here, I just simply introduce the popular elements. And so basically, we know for the compounds, some are basic, some are acid. So for the no metals, they are easy to become the acid, and for the no metals, they tend to form basic. Okay, yeah, have a look at it.